let's draw now the situation when she's arrived at Proxima Centauri. Here's the rocket ship, and there's the frame going off in front and behind. And she turns the rocket ship around to fly back. So if beta was in this direction, 0.95 on the way out, now it's minus 0.95 or oppositely directed. And the key point here is that these two frames, the inbound and outbound frame, are different frames. So to be clear, we'll call this S double prime, if this was S prime, and we're going to take delta x double prime is equal to delta x prime is equal to 0, and delta t double prime is equal to delta t prime is equal to 1.41 years when she arrives. And when she gets back to Earth, delta t prime, double prime, will be 2.42 years. Okay, this will be the return at Earth. Okay, so why is it 2.42? Well, we can think back to how we calculated the 1.41. That involved the Lorentz transformation, or sorry, the Lorentz contraction of the distance, and it depended upon gamma. And the gamma goes like 1 over the square root of 1 minus beta squared. It only depends on the square of beta. So whether beta is plus or minus makes no difference. It's the same value of gamma. So she's now moving with beta of 0.95. She sees the same contracted distance, so the time it takes has to be exactly equal to the time it took her to go out. So the total will be 2.42. So there's no question that she believes her clock will read 2.42 when it finally arrives back at Earth. Okay, now when she arrives at Earth, the tower clock, in other words, the clock here, will now read the full trip journey. So that's 9.06 years. Okay, and so it would, and so that this is also can be understood from symmetry. The trip out involved the distance and beta, and the value of beta switches, but the distance is the same, so it's just twice the original distance, twice the original time. So it's again a symmetry effect. Okay, so here's the one thing that is a little bit odd. When she turned around, we had her read the clock at the Earth frame, and she read 0.44 years. Okay. However, the question is, what does that clock read as soon as she jumps from frame S prime to S double prime? And the answer is that it's going to read a lot different than 0.44. In other words, it's going to actually read the total trip, 9.06, minus 0.44 years. So it will read 8.62 years at the turnaround. So this is very odd, and this has to do with the fact that the two frames, S prime and S double prime, are different frames, and simultaneity in one frame does not imply simultaneity in the other frame. And in fact, her arrival at PC in one frame does not imply that they both frames have the same clocks elsewhere at the Earth frame. So we've set it to be 0.44 years when she jumps from S prime to S double prime, but in fact there's a huge jump in the value of her co-conspirators' readings at the Earth frame. So there's one way to think about this in diagrammatic form, and we'll talk about this in more detail. this is a space-time diagram, T and X, and her trip out to Proxima Centauri is something that looks like a line. This is the origin, is where she starts at the Earth. This is where PC is. And then she returns back to the Earth, and she reaches that point at some later time. And what we've really said is that her frame reads 0.44 on the outbound. So you think about this being the outbound frame of simultaneity, equal times. And when she actually arrives at PC, that line of simultaneity extends to the point 0.44 at the Earth. But on the outbound, there's another frame, okay? And this frame is the inbound frame. And the lines of simultaneity for it are very different. And so as soon as she goes from one frame to the other, it appears that the clocks shift forward to the time 8.62 years. And when she finally gets back, it's the full trip, 9.06 years. So there is a very dramatic swing in the clock that she associates with Earth when she switches